two whole numbers and one simple question. Does the first one divide the second one exactly? That small question grows into the mathematics that keeps your bank details safe. This chapter is about whole numbers and about the secret codes we build from them. Let's get started. Hello and welcome to Chapter 4. In this chapter we study number theory and cryptography. Number theory is the math of whole numbers. Cryptography is the art of secret codes. We start small with when one number divides another. Then we build up step by step to primes, to greatest common divisors, and at the end to the math behind secret messages on the internet. Let's begin. Let's see why this chapter matters. Number theory is the part of math that studies the integers. Integers are the whole numbers like -2, 0, 1, and 100. We look at their properties. One big idea is divisibility. That means, does one number divide another with no remainder? Another big idea is which numbers are prime. We also learn to write numbers in other bases, like binary, which is base 2, and hexadecimal, which is base 16. People have loved number theory for a long time. The ideas are beautiful, they are easy to start, and many questions are still open, still unsolved. We will reuse the proof methods from Chapter 1. For a long time people thought number theory was pure math, with no use, but today it sits at the heart of computer science and cryptography. We cover those in sections 4.5 and 4.6. This is the plan for the whole chapter. 6 topics, and each one builds on the one before it. First, divisibility and modular arithmetic. Second, how to represent integers in different bases, and the algorithms for that. Third, primes and greatest common divisors. Fourth, solving congruences. Fifth, applications of congruences. And sixth, cryptography, so let's take them in order. Section 4.1, Divisibility and Modular Arithmetic. In this section, we learn what it means for one integer to divide another. We meet the division algorithm, which gives a quotient and a remainder. And we learn modular arithmetic, which is arithmetic that wraps around, like the hours on a clock. This section has 3 parts. First, division, and what it means for one number to divide another. Second, the division algorithm, which is really a theorem about quotients and remainders. And third, modular arithmetic, which is arithmetic with remainders. Let's define division. Take 2 integers A and B and say it is not 0. We say it divides B if we can find an integer C so that B equals a times C in plain words. B is a whole number of copies of A. When this happens, we call a factor or a divisor of B, and we call B a multiple of A. We write it with a vertical bar. The bar means it divides B. If it divides B, then B over A is a whole number with no remainder. If it does not divide B, we put a slash through the bar. Let's work this one step at a time. We ask whether 3 divides 7 and whether 3 divides 12. Step 1, set it up. The number doing the dividing is 3, so we ask, is there a whole number C with B equal to 3 times C? Step 2, try B equal to 7. 7 divided by 3 is 2.33. Step 3, that is not a whole number, so no C works. 3 does not divide 7. Step 4, now try B equal to 12. 12 divided by 3 is 4. Step 5, 4 is a whole number, so 12 equals 3 times 4 and 3 divides 12. Now some rules about divisibility. Theorem 1. Let a b and c be integers with a not 0. Part 1. If a divides b and a divides c, then a divides b plus c. Part 2. If a divides b, then a divides b times c for any integer c. Part 3. If a divides b and b divides c, then a divides c. The book leaves parts 2 and 3 as exercises. We will prove part 1 together on the next slide. First, set it up. We are given that a divides b and a divides c by the definition. That means we can write b as a times s and c as a times t, where s and t are whole numbers. What we must show is that a divides b plus c. Now the working. Line 0 is the number we care about, b plus c. Step 1, putting what we know. B is a s and c is a t, so the sum is a s plus a t. Step 2, both terms have an a in them. Factor it out. We get a times in brackets s plus t. Step 3, s plus t is a whole number. So b plus c is a whole number of copies of a. That is exactly what a divides b plus c means. Theorem 1 has a useful corollary. If a divides b and a divides c, then it also divides m times b plus n times c for any whole numbers m and n. A sum like m times b plus n times c is called a linear combination of b and c, so the short version is this. A number that divides both b and c divides every linear combination of them. We will lean on this idea many times in this chapter. When you divide one whole number by a positive whole number, you get a quotient and a remainder. People call it the division algorithm, but really it is a theorem. Take an integer a and a positive integer d, then there are unique integers q and r, where r is at least 0 and less than d, so that it equals d times q, plus r. Notice the word unique. There is only one pair that works. And notice the range on r, the remainder is never negative, and never as big as d. Let's name the 4 parts of that equation, one at a time. D is the divisor. It is the number we divide by. I is the dividend. It is the number being divided. Q is the quotient. We write it as a div d. R is the remainder. We write it as a mod d. So div gives you the whole part and mod gives you what is left over. Both are functions. You feed them 2 numbers and they hand back 1. Let's work a division, step by step. We divide 101 by 11. Step 1, set it up. The dividend a is 101. The divisor d is 11. Step 2, ask how many whole 11s fit inside 101. 11 times 9 is 99. 10 11s would be 110, which is too big. So 9 is the answer. Step 3, subtract. 101 minus 99 leaves 2. Step 4, check the remainder is in range. It must be at least 0 and less than 11. 2 passes. Step 5, read it off. The quotient 101 div 11 is 9. The remainder 101 mod 11 is 2. Negative numbers need care, so let's go slowly. We divide minus 11 by 3. Step 1, set it up. The dividend a is minus 11. The divisor d is 3. Step 2, now the mistake people often make. Minus 11 equals 3 times minus 3 minus 2. That gives a remainder of minus 2, but the rule says the remainder must be 0 or more, so this is not allowed. Step 3, take the quotient 1 step further down. 3 times minus 4 is minus 12. Step 4, now subtract. Minus 11 minus minus 12 is plus 1. The leftover is positive. Step 5, read it off. The quotient is -4. The remainder is 1, not -2. Now the congruence relation. This is a key idea for the whole chapter. Take two integers L and B and a positive integer m. We say it is congruent to b, modulo m, if m divides the difference, a minus b. We write it like this. A is congruent to b, mod m. The equal sign has 3 bars, not 2. The number m is called the modulus. If they are not congruent, we put a slash through the 3-bar sign. This is a nice way to feel what congruence means. Two numbers are congruent mod m exactly when they leave the same remainder after dividing by m, so congruence sorts every integer into buckets, 1 bucket per remainder. The clock is the right picture. On a 12-hour clock, 3 o'clock and 15 o'clock point at the same spot. The difference is 12, and 12 is our modulus. So the two numbers are congruent mod 12. Let's test a congruence, step by step. Step 1, set it up. A is 17, b is 5, the modulus m is 6. Step 2, the test asks whether m divides a minus b, so take the difference. 17 minus 5 is 12. Step 3, does 6 divide 12? Yes, because 12 is 6 times 2. Step 4, the test passes, so 17 is congruent to 5 mod 6. Now one that fails, so you can see the difference. Step 1, set it up. A is 24, b is 14, the modulus m is 6. Step 2, take the difference. 24 minus 14 is 10. Step 3, does 6 divide 10? No, 10 over 6 is not a whole number. Step 4, the test fails, so 24 is not congruent to 14 mod 6. Let's dig deeper into congruences. Theorem 4. Let m be a positive integer. Then a and b are congruent mod m, if and only if there is an integer k so that a equals b plus k times m. In plain words, a and b are congruent exactly when they differ by a whole number of steps of size m, so you can hop from b to a by taking k steps. Each of size m, the number k may be negative, which just means hopping backwards. And if and only if has 2 directions, so we set it up as 2 little proofs. This is the first one. Line 0, assume is congruent to b mod m. Step 1, by the definition of congruence, m divides a minus b. Step 2, if m divides a minus b, then a minus b equals k times m for some whole number k. Step 3, move the b across to the other side. That gives a equals b plus k times m direction one is done. Now the second direction, and we run the same reasoning backwards. Line 0, assume a equals b plus k times m. Step 1, move the b across, so a minus b equals k times m. Step 2, that says a minus b is exactly k copies of m, so m divides a minus b. Step 3, and by the definition that means a is congruent to b, mod m both directions hold, so the theorem is proved. Careful, the word mod shows up in 2 ways, and they mean different things. In a is congruent to b, mod m, the word mod is part of a relation. It tells you whether 2 numbers are related, yes or no. But in a mod m equals b, the word mod is a function. It takes a number and gives back a remainder. Theorem 3 ties the 2 together. A is congruent to b, mod m, if and only if a mod m equals b mod m, so the relation holds exactly when the 2 functions give the same answer. The proof is left as an exercise. This next result is very useful. Congruences behave well with addition and multiplication. Theorem 5. Suppose it is congruent to B, mod M, and C is congruent to D, mod M then a plus C is congruent to B plus D, and a times C is congruent to B times D. The practical meaning is simple. Inside a congruence you may swap any number for another one congruent to it, and the congruence still holds. Set it up first. By Theorem 4 we can write B as a plus S times M, and D as C plus T times M, where S and T are whole numbers. Line 0. Look at the sum on the right-hand side, B plus D. Step 1. Put in what B and D are. Step 2. Regroup. Collect A and C together and pull the M out of the other two terms. We get a plus C plus M times S plus T. Step 3. So B plus D and a plus C differ by a multiple of M. That is exactly what the congruence says. Now the product with the same setup. Line 0. Look at B times D. Step 1. Put in what B and D are. So we have in brackets a plus SM times in brackets C plus TM. Step 2. Multiply it out. One term is a times C, every other term has an M in it, so pull the M out. We get a C plus M times a T plus CS plus STM. Step 3. So BD and a C differ by a multiple of M, that means a C is congruent to BD, mod M. Set it up. The modulus is 5. 7 is congruent to 2, mod 5, because 7 minus 2 is 5. And 11 is congruent to 1, mod 5, because 11 minus 1 is 10. Now the sum, line 0, 7 plus 11. Step 1. Theorem 5 lets us swap each side for something congruent. So swap 7 for 2 and 11 for 1. We get 2 plus 1. Step 2. That is 3 mod 5. Check it. 7 plus 11 is 18, and 18 mod 5 is 3. It agrees. Now the product. Line 0, 7 times 11. Step 3. Swap each side again. We get 2 times 1. Step 4. That is 2 mod 5. Check it. 7 times 11 is 77, and 77 mod 5 is 2. It agrees. When you have a true congruence, you may do two things safely. First, you may multiply both sides by any whole number and it stays true. Second, you may add any whole number to both sides. That also keeps the congruence true. Both come straight from Theorem 5. Taking D equal to C but dividing is a different story, and the next slide shows why. Let's watch division break a congruence. Line 0. 14 is congruent to 8 mod 6. This is true because 6 divides 14 minus 8, which is 6. Step 1. Divide the left side by 2. 14 over 2 is 7. Step 2. Divide the right side by 2. 8 over 2 is 4. Step 3. Now test the new pair. 7 minus 4 is 3. Step 4. Does 6 divide 3? No. So 7 is not congruent to 4 mod 6. Dividing broke a true congruence. In section 4.3, we learn the exact condition that makes division safe. Sometimes the numbers are large. We do not want to add or multiply them in full. This corollary is a shortcut. To find the sum mod m, first take each number mod m, then add those small remainders. Then take mod m once more. The product works the same way. Take each number mod m, multiply the two small remainders, then take mod m again. The point is that every number stays small along the way. Let's give this arithmetic a name. Z sub m is the set of whole numbers from 0 up to m minus 1. So for 11, The set is 0 through 10. Addition mod m. Add the two numbers the normal way, then take mod m. Multiplication mod m. Multiply the two numbers, then take mod m. Working this way is called Arithmetic Modulo. The nice part is that every answer lands back inside the set. Set it up. The modulus is 11, so every answer must land in the set 0 through 10. Line 0. We want 7 plus sub 11, 9. Step 1. By the definition, that is 7 plus 9, then mod 11. Step 2. 7 plus 9 is 16. 16 mod 11 is 5, because 16 is 111 plus 5. Now the product. Line 0, 7 times sub 11, 9. Step 3. By the definition, that is 7 times 9, then mod 11. Step 4. 7 times 9 is 63. 63 mod 11 is 8, because 63 is 5 11s, 55 plus 8. Both answers sit inside the set just as promised. This new arithmetic behaves a lot like normal arithmetic. First, closure. If you add or multiply two members of the set, the answer is still in the set. It never escapes. Second, associativity. The grouping does not matter. You may combine the first two first or the last two first, and the result is the same. This holds for both plus and times. Two more properties. Commutativity. The order does not matter. A plus b equals b plus a, and a times b equals b times a. Identity elements. 0 is the do-nothing element for addition. Adding 0 changes nothing. 1 is the do-nothing element for multiplication. Multiplying by 1 changes nothing. Both live inside the set, so we never have to leave. Two more. Additive inverse. Every element has a partner that brings it back to 0. If it is not 0, its partner is m minus a. Add them and you get 0. And 0 is its own partner. Distributivity. Multiplication spreads over addition, just like normal. A times the sum of b and c equals a times b, plus a times c. The book leaves the proofs as exercises 42 through 44. Now a warning. Look back at that list of properties. One familiar thing is missing. We did not list multiplicative inverses, and they do not always exist. For example, take 2 mod 6. There is no number you can multiply by 2 mod 6 to land on 1. Try them all. 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 0, and so on. 1 never appears. So 2 has no multiplicative inverse mod 6. In section 4.4, we find the exact condition. It depends on the greatest common divisor of an m. Section 4.2, Integer Representations and Algorithms. So far we studied divisibility and modular arithmetic. Now we ask a new question. How do we actually write down a number, and how does a computer store it? We will see base 10, base 2, base 8, and base 16. We will also learn fast algorithms for adding, multiplying, and taking powers. This is our plan for this section. First, integer representations. We will write numbers in base B, in binary, in octal, and in hexadecimal. Second, a base conversion algorithm, a step-by-step recipe to change a number from one base to another. Third, algorithms for integer operations, the methods a computer uses to add, multiply, and take powers. We write numbers in base 10 every day. Base 10 means each place is a power of 10. Take 965. The 9 is in the hundreds place, so it means 9 times 10 squared. The 6 is in the 10's place, so 6 times 10. The 5 is in the 1's place, so 5 times 1. Add them and you get 965. But 10 is not special. We can use any base b bigger than 1. 3 bases matter most for computers. Base 2 called binary, base 8 called octal, and base 16 called hexadecimal. History is fun here. The ancient Maya used base 20. The ancient Babylonians used base 60. And that choice is still with us. Base 60 is the reason we count 60 minutes in an hour and 60 seconds in a minute. A 4,000-year-old habit still on your wrist. Why can we use any base b bigger than 1? Because of Theorem 1. Take any base b bigger than 1, then every positive integer n can be written as a sum. Each term is a digit times a power of b. The digits are whole numbers from 0 up to b minus 1, and the leading digit is not 0. The important word is uniquely. There is only one such expansion for each number. We prove this by induction in section 5.1. Now the notation. The numbers a sub j are called the base b digits. The whole thing is called the base b expansion of n. We write it as the string of digits inside parentheses, with a small b below. So the little b at the bottom right tells you which base you are reading. For base 10, we usually drop the little 10, because base 10 is our default. Binary is base 2. Most computers store integers this way. It uses only 2 digits, 0 and 1. Computers love binary because a wire is either on or off, nothing in between. Each place in a binary number is a power of 2. Reading from the right, the places are 1, 2, 4, 8, 16, and so on. Each step to the left doubles. To read a binary number, you add up the places that hold a 1. Set it up. Count the bits. There are 9 of them, so the places run from 2 to the 8th on the left down to 2 to the 0 on the right. Line 0. This is the number we convert. Step 1. Write the top 4 places. 1 times 2 to the 8th plus 0 times 2 to the 7th plus 1 times 2 to the 6th plus 0 times 2 to the 5th. Step 2. Now the low 5 places. All of them hold a 1. Step 3. Throw away every place that holds a 0 and write the values of the rest. 2 to the 8th is 256. 2 to the 6th is 64. Then 16, 8, 4, 2, and 1. Step 4. Add them all up. The answer is 351. This one is shorter, so you can see the whole shape at once. 5 bits, so the places run from 2 to the 4th down to 2 to the 0. Line 0. The number is 11011 in binary. Step 1. Write it place by place. 1 times 16 plus 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1. Step 2. The 4 place holds a 0, so it drops out. That leaves 16 plus 8 plus 2 plus 1. Step 3. Add them. The answer is 27. Octal is base 8. It uses 8 digits, 0 through 7. There is no digit 8 and no digit 9 in octal. Each place is a power of 8. Reading from the right, the places are 1, then 8, then 64, then 512. Each step to the left multiplies by 8. Set it up. There are 4 digits, so the places are 8 cubed, 8 squared, 8, and 1. Line 0. Our number is 7016 in octal. Step 1. Write it place by place. 7 times 8 cubed plus 0 times 8 squared plus 1 times 8 plus 6 times 1. Step 2. 8 cubed is 512. The second term is 0, so it drops out. Step 3. 7 times 512 is 3,584. The small terms add to 14. Step 4. Add them. The answer is 3,598. This one is small. 111 in octal. 3 digits, so the places are 64, 8, and 1. Step 1. Write it place by place. Step 2. Work out the powers. 64 plus 8 plus 1. Step 3. Add them. The answer is 73. Now notice something. The same 3 digits mean different things in different bases. 111 in octal is 73, but 111 in binary is only 7. The digits alone are not enough. You must know the base. Hexadecimal is base 16. It needs 16 different digits, but we only have 10 number symbols, 0 through 9, so we borrow 6 letters. Look at the table. A means 10, B means 11, C means 12, D means 13, E means 14, and F means 15. So the full digit set runs 0 through 9, then A through F. Set it up. There are 5 digits, so the places run from 16 to the 4th down to 16 to the 0, and translate the letters first. A is 10, E is 14, B is 11. Line 0. Our number is 2, a E0B in hexadecimal. Step 1. Write the top 3 places. 2 times 16 to the 4th plus 10 times 16 cubed plus 14 times 16 squared. Step 2. Then the low 2 places. 0 times 16 plus 11 times 1. Step 3. Work out each term. 130,1072 plus 40,960 plus 3,584 plus 0 plus 11. Step 4. Add them up. The answer is 175,627. One more short one. E5 in hexadecimal. 2 digits, so the places are 16 and 1. Step 1. E stands for 14, so we have 14 times 16 plus 5 times 1. Step 2. 14 times 16 is 224 plus 5. Step 3. Add them. The answer is 229. Let's learn how to change a number into another base. Say we want the base be form of an integer, and the trick is simple. We divide again and again by b, and we keep the remainders. Step 1. Divide n by b. We get a quotient q0 and a remainder a 0. That first remainder is the rightmost digit of the answer. Step 2. Now take the quotient q0 and divide it by b. The new remainder, a 1, is the next digit, the second one from the right. Step 3. Keep going. Each time, divide the newest quotient by b and write down the remainder. Step 4. Stop when the quotient reaches 0. Then read the remainders from the bottom back up to the top. This is the same method written as an algorithm. Let's read it slowly. We start by setting q to n and k to 0. The variable q holds the current quotient. The variable k counts the digits. The while loop runs as long as q is not 0. Inside, we do 2 things. First, a sub k becomes q mod b, that is the remainder, our next digit. Second, q becomes q div b, that is the new quotient, the whole part of q divided by b, then we add 1 to k. When q reaches 0, the loop stops. We return the digits a sub k minus 1 down to a sub 0. Read together. They form the base b expansion of n. set it up. Octal means base 8. We start with Q equal to 12,345, and we divide by 8 each round. Round 1. 12,345 equals 8 times 1,543 plus 1. The digit is 1. Round 2. Divide 1,543 by 8. It equals 8 times 192 plus 7. The digit is 7. Round 3. Divide 192 by 8. It equals 8 times 24 plus 0. The digit is 0. Round 4. Divide 24 by 8. It equals 8 times 3 plus 0. The digit is 0. Round 5. Divide 3 by 8. The quotient is 0 and the remainder is 3. The quotient hit 0, so we stop. Now read off the answer. The remainders came out from right to left, so we read them from the bottom of the table back up to the top. That gives 30071. So the octal form is 30071. Always check your work. 3 times 8 to the 4th is 12,288. 7 times 8 is 56, plus 1. Add them and you get 12,345, which is the number we started with. It checks out. This table lines up 4 bases side by side for the numbers 0 through 7. The top row is decimal, our everyday base 10. Then hexadecimal base 16. For 0 through 7 it looks exactly the same. Then octal base 8, again the same digits. And last, binary base 2. Binary runs out of digits after 1. It writes 2 as 10 and 4 as 100. So for the first 8 numbers, decimal, hexadecimal, and octal all agree. Nothing has run out yet. They only differ once a base runs out of digits. Now the second half, 8 through 15. Here the bases part company. The top row is decimal again, 8 through 15. Look at hexadecimal. After 9 it needs new symbols, so it uses letters. A stands for 10, B for 11, C for 12, D for 13, E for 14, and F for 15. Look at octal. It ran out at 7, so 8 is written 10. Then it runs on up to 17 for 15. Look at binary. Every number from 8 to 15 takes exactly 4 bits, from 1000 up to 1111. This is the key point behind that table. 8 is 2 cubed. So each octal digit is worth exactly 3 binary digits. 16 is 2 to the 4th. So each hexadecimal digit is worth exactly 4 binary digits. Because of this neat fit, changing between binary, octal, and hexadecimal needs no arithmetic at all. You only regroup the bits. Group them in 3s for octal, or in 4s for hexadecimal. Let's find the octal form of a long binary number. Step 1. Set it up. Octal needs blocks of 3 bits and we always count from the right. Our number has 14 bits, which is not a multiple of 3. The next multiple up is 15. Step 2. So we pad 10 on the front, then cut the bits into blocks of 3. We get 0, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0. Step 3. Read each block as a single octal digit. 0, 1, 1 is 3, 1, 1, 1 is 7, 0, 1, 0 is 2, 1, 1, 1 is 7 again, 1, 0, 0 is 4. Step 4. Write them in order. The octal answer is 37274. Same bits, different grouping. Now we want the hexadecimal form. Step 1. Set it up. Hexadecimal needs blocks of 4 bits, again counted from the right. We have 14 bits, so we round up to 16. Step 2. Pad 2 zeros on the front, then cut into 4s. We get 0, 0, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0. Step 3. Read each block as one hex digit. 0, 0, 1, 1 is 3. 1, 1, 1, 0 is 14, which is E1, 0, 1, 1 is 11, which is B1, 1, 0, 0 is 12, which is C. Step 4. Write them in order. The hexadecimal answer is 3, E, B. See, notice how the very same bits gave two different answers, just by grouping them in 3s or in 4s. Computer chips work in binary, so we need algorithms that add binary numbers bit by bit. Each binary digit is called a bit. This is the addition algorithm. We add two numbers A and B given by their bits. We keep a carry called C and set it to 0 at the start. The for loop walks through the bit positions from j equals 0 up to n-1, that is from right to left. At each position we add three things: bit A sub j, bit B sub j, and the carry C. From that sum we get two pieces. The new carry D is the floor of the sum divided by 2. Floor means round down. The sum bit S sub j is the sum minus 2 times D, then the carry C becomes D, ready for the next position. After the loop, the final carry becomes the top bit. S sub n, then we return the bits the way we write numbers, top bit first. Now how much work is that? Adding two n-bit integers takes big O of n-bit additions. Why? At each bit position we do the same small job. Add 3 bits, work out one carry, write one sum bit. Nothing in that job gets bigger as the numbers get longer, and there are n positions. So adding twice as many bits takes about twice as long. Now the multiplication algorithm. We multiply two numbers A and B, again given by their bits, using shifted partial products. The first loop builds the partial products. For each bit position j of B, we look at bit B sub j. If that bit is 1, the partial product C sub j is a shifted left by j places. Shifting left by j places is the same as multiplying a by 2 to the j. If the bit is 0, the partial product C sub j is just 0. So we get n partial products, C sub 0 up to C sub n-1. The second loop adds them all together. We start P at 0, then add each partial product in turn. At the end, P holds the product of times B. And what does multiplication cost? Multiplying two n-bit integers takes big O of n² bit additions. Counted in two parts. There are n partial products, one for each bit of B, and adding each partial product costs about n-bit operations, as we just saw. Multiply the two counts together. N times n is n², so multiplication is much more expensive than addition. In cryptography, we often need b to the power n, mod m, where b, n, and m are all huge. We need a fast way to do this. The trick uses the binary form of the exponent n. Look at the boxed identity. Because the exponent n is a sum of powers of 2, b to the n splits into a product. Each factor is b raised to one of those powers of 2. And a factor only appears when the matching bit is a 1. So the power splits into one factor per bit, that is 1. So to build b to the n, we only need a short list of values. Start with b, square it to get b². Square that to get b to the 4th. Square again for b to the 8th, and keep going. Each one is the square of the one before, so each costs a single multiplication. Then we multiply together just the terms where the matching bit is 1, and skip the rest. That is why this is fast. Instead of n multiplications, we need about log n of them. Set it up. 11 in binary is 1, 0, 1, 1. The bits that are 1 sit at positions 0, 1, and 3. Position 3 means 3 to the 8th. Position 1 means 3 squared. Position 0 means 3 to the 1st. Line 0, we want 3 to the 11th. Step 1, so it equals 3 to the 8th times 3 squared times 3. Check the exponents. 8 plus 2 plus 1 is 11. Step 2, we build 3 to the 8th by squaring 3 times. 3 squared squared squared. Step 3, 3 squared is 9. 9 squared is 81. Step 4, 81 squared is 6,561, which is 3 to the 8th. Step 5, multiply the 3 pieces. The answer is 177,147, and notice the cost. We used 3 squarings and 2 more multiplications. That is 5 in all, instead of the 10 we would need by multiplying by 3 over and over. This algorithm puts the idea to work, and it keeps every number small by taking mod m at each step. We keep 2 variables. The answer x starts at 1. The variable power starts at b mod m. The for loop runs over the bits of n, from bit 0 up to bit k minus 1. At each step we check the current bit of sub I. If that bit is 1, we fold power into the answer. X becomes x times power, mod m. Then whether the bit was 1 or 0, we square power. So power moves from b to b squared to b to the 4th, and so on, each time reduced mod m when the loop ends. X holds b to the n, mod m. How fast is this? The cost is order the square of log m times log n bit operations. First, every number stays below m, because we reduce mod m after each multiplication. So the numbers never grow, however large the exponent is. Second, the loop runs once per bit of the exponent n, which is about log n times, not n times. That is the difference between a few thousand steps and a hopeless number of steps. This is what makes public key cryptography practical. Section 4.3, Primes and Greatest Common Divisors. Now we turn to the building blocks of the integers. A prime number cannot be split into a product of smaller numbers. We will study primes, some famous open questions about them, and the greatest common divisor of 2 numbers. This is our plan for this section. First, we meet prime numbers and their main properties. Then we look at some famous conjectures and open problems about primes, questions that are still not answered. Next, we study the greatest common divisor and the least common multiple of 2 numbers. After that comes the Euclidean algorithm, a fast way to find the greatest common divisor. Finally, we see how to write a greatest common divisor as a linear combination of the 2 numbers. Let's define a prime number. A prime is a positive integer p bigger than 1, whose only positive factors are 1 and p itself. In other words, nothing else divides it evenly. A positive integer bigger than 1 that is not prime is called composite. Composite means it can be broken into smaller factors. And notice that 1 is neither prime nor composite. It is left out on purpose, and we will see why shortly. Let's test 2 numbers step by step. Step 1, set it up. To decide, we hunt for a factor strictly between 1 and the number itself. If we find one, the number is composite. Step 2, try 7. Test 2, 3, 4, 5, and 6. None of them divides 7 evenly. Step 3, so only 1 and 7 are left as factors. 7 is prime. Step 4, now try 9. 2 does not divide 9, but 3 does. 9 equals 3 times 3. Step 5, we found a factor other than 1 and 9, so 9 is composite. This is one of the biggest ideas in number theory. Take any whole number bigger than 1. You can break it into prime pieces, and there is only one way to do it once you list the pieces from small to large. We call this the unique prime factorization. Think of primes as atoms. Every number is built from these atoms, and the recipe is unique. Let's see the theorem at work, one number at a time. 100 equals 2 times 2 times 5 times 5. We write that as 2 squared times 5 squared. 2, 641 is a prime, so it stands alone. To be sure, we try the primes up to 25. 2, 3, 5, 7, 11, 13, 17, 19, and 23. None of them divides it, and 26 squared is already bigger than 641, so there is nothing left to try. 999 equals 3 times 3 times 3 times 37. That is 3 cubed times 37. 1024 is 2 multiplied by itself 10 times, which we write as 2 to the 10th. Same number, 1 factorization each. No other recipe exists. This is a simple old method to find primes, named after Eratosthenes, a Greek scholar. The word sieve means a filter, like a kitchen strainer. It keeps the good bits and lets the rest fall through. Write the numbers from 2 to 100. We leave 1 off the list because 1 is neither prime nor composite. Step A, keep 2, but cross out every other multiple of 2, 4, 6, 8, and so on. Step B, keep 3, but cross out every other multiple of 3. Step C, keep 5, and cross out its other multiples. Step D, keep 7, and cross out its other multiples. Step E, now stop. Every number still standing is prime. In a moment we will see why 4 rounds were enough. Eratosthenes lived in the 3rd century before the Common Era. He ran the great library at Alexandria, and he also measured the size of the earth. His sieve still works today. And this is what it gives us. The primes up to 100 are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97. 25 primes in the first 100 numbers. Look at the grid. It shows 1 to 100 in 10 rows of 10. The green cells are the primes. The gray cells are composite numbers that the sieve crossed out. The cell for 1 is pale, because 1 is neither prime nor composite. Notice how the green cells thin out as you go down the grid. The primes get rarer, but they never stop. Now, why did we only sieve with 2, 3, 5, and 7? This is the key fact. If a number n is composite, then it must have a prime divisor no bigger than the square root of n. The reason is simple. Suppose n equals a times b. The two factors cannot both be larger than the square root of n, because their product would then be larger than n, so at least one of them is small. Apply that here. The square root of 100 is 10, so every composite number up to 100 has a prime factor below 10. The primes below 10 are 2, 3, 5, and 7. 4 rounds and we are done. That same fact gives us a test called trial division. Take a number n bigger than 1. Try every integer I from 2 up to the square root of n, and check whether it divides n we start at 2, because 1 divides everything and would tell us nothing. If none of them divides n, then n is prime. Trial division is correct, and it is easy to write, but it is very slow when n is large. For a number with 200 digits, the square root still has 100 digits, and no computer can count that far. That is exactly why cryptography needs the clever tests we meet later. Can we ever run out of primes? No. Euclid showed there are infinitely many, and his proof is famous. Let's set it up carefully. We argue by contradiction. That means we assume the opposite of what we want and then show that the assumption breaks. So suppose for a moment that there were only finitely many primes. Then we could list every one of them, P1, P2, and so on up to Pn. Remember that list. On the next slide, we build a number that ruins it. Now the working, one step at a time. Step 1. Build a new number q, multiply every prime on the list together, then add 1. Step 2. Think about q by the fundamental theorem of arithmetic. Q is either prime or it breaks into primes. Step 3. Now the trick. None of our listed primes can divide q if some prime pj divided q. It would also have to divide q minus the product of all the primes. But that difference is exactly 1, and no prime divides 1. Step 4. So there must be a prime that is not on our list. Either q itself is that prime, or one of its prime factors is. Step 5. That breaks our assumption that the list held every prime. The assumption was wrong, so there are infinitely many primes. This proof is more than 2,000 years old. It comes from Euclid's Elements. Mathematicians still admire it because it is short, complete, and surprising. Paul Erdos, a Hungarian mathematician of the 20th century, liked to speak of the book. In his joke, God keeps a book that holds the most perfect proof of every theorem. A mathematician's highest praise was to say that a proof was from the book. Euclid's proof is the first entry. Some primes have a special shape. Take 2, raise it to a prime power p, then subtract 1. If the result is prime, we call it a Mersenne prime, after the French monk Marin Mersenne. Let's try small primes for p. P equals 2. 2 squared minus 1 is 3, prime. P equals 3. 2 cubed minus 1 is 7, prime. P equals 5. 2 to the 5th minus 1 is 31, prime. P equals 7. 2 to the 7th minus 1 is 127, prime. Now P equals 11. 2 to the 11th minus 1 is 2047, and that is not prime. It equals 23 times 89, so a prime exponent does not guarantee a Mersenne prime. Why do we care about numbers of this shape? Because there is a fast test that decides whether 2 to the p minus 1 is prime. No such fast test exists for numbers in general, so the record holders are almost always Mersenne primes. Back in 2011, 47 Mersenne primes were known. The largest was 2 to the power 43,112,609 minus 1. Written out, it has almost 13 million digits. People hunt for new ones together in a shared project called GIMPS, which stands for the Great Internet Mersenne Prime Search. Anyone can lend a computer to it. How thick or thin are the primes as numbers get large? This question kept mathematicians busy for a long time. The answer is the prime number theorem, proved in the 1800s. Count the primes up to some number x. The theorem says this count is close to x divided by the natural log of x, and the bigger x gets, the better the estimate becomes. There is a nice way to feel this. Pick a random whole number below, and the chance it is prime is about 1 over the natural log of n. So as numbers grow, primes get rarer, but only slowly. Making large primes is useful, and we will need them for secret codes in section 4.6. So it would be lovely to have a formula that always spits out primes. Sadly, no simple one exists. And more than that, no non-constant polynomial with whole number coefficients does either. We do have to say non-constant. The polynomial that always returns 2 is a silly exception, since 2 is prime. The good news is that later we can build numbers that are almost certainly prime, which is enough for cryptography. This story is worth remembering. Take f of n equals n squared minus n plus 41. Try n from 1 up to 40. Every single answer is prime, 40 times in a row. You might feel quite sure the rule always works. Pause the video and guess. Does it still give a prime at 41? Now try n equals 41. You get 41 squared minus 41 plus 41. The last two terms cancel. So the answer is 41 squared, which is 41 times 41, clearly not prime. So a rule can pass 40 tests in a row and still fail on the next one. Evidence is not proof. That is why we prove things. Primes still hide many secrets. Even after centuries of study, many questions about them are unresolved. This is the most famous open question. Goldbach's conjecture says every even number bigger than 2 is the sum of two primes. For example, 10 is 3 plus 7. 20 is 3 plus 17. Computers have checked this for every even number up to 1.6 times 10 to the 18. That is a huge range, and no exception has ever turned up. Most mathematicians believe it is true, but nobody has proved it. Two more open questions. First, numbers of the form n squared plus 1. We think infinitely many of them are prime, but that is unproven. What we do know is a weaker result. Infinitely many are either prime or a product of at most two primes. Second, the twin prime conjecture. Twin primes are two primes just 2 apart, like 3 and 5 or 11 and 13. We believe there are infinitely many such pairs. Again, no proof. But people do find enormous examples. The record pair from 2011 had over 100,000 digits in each member. Suppose you have two whole numbers. A common divisor is a number that divides both of them evenly. The greatest common divisor is the biggest such number. We write it as GCD of A and B. For small numbers, you can simply look at the factors and pick the biggest shared one. For big numbers, we will need an algorithm, and we build one later in this section. Let's find two greatest common divisors, step by step. Step 1. Set it up. List the positive divisors of each number, then take the largest one they share. Step 2. The divisors of 24 are 1, 2, 3, 4, 6, 8, 12, 24. The divisors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, 36. Step 3. The shared ones are 1, 2, 3, 4, 6, and 12. The largest is 12, so the greatest common divisor of 24 and 36 is 12. Step 4. Now the second pair. 17 is prime, so its only divisors are 1 and 17, and 17 does not divide 22. Step 5. So the only shared divisor is 1. The greatest common divisor of 17 and 22 is 1. This special case is worth a name. When the greatest common divisor of two numbers is 1, we say they are relatively prime. It means they share no common factor except 1. For example, 17 and 22 are relatively prime, as we just worked out. Now suppose you have not two numbers but a whole list. We say the list is pairwise relatively prime if every pair inside it is relatively prime. Take any two members of the list, and their greatest common divisor must be 1. Notice the word every. One bad pair spoils it. Let's test a list, step by step. Step 1, set it up. 3 numbers give 3 pairs. We must check all 3, 10 and 17, 10 and 21, and 17 and 21. Step 2, the greatest common divisor of 10 and 17 is 1. 17 is prime and does not divide 10. Step 3, the greatest common divisor of 10 and 21 is 1. 10 is 2 times 5. 21 is 3 times 7. Nothing shared. Step 4, the greatest common divisor of 17 and 21 is 1. Step 5, every pair gives 1. So yes, this list is pairwise relatively prime. Now a list that fails. Step 1, set it up. Again 3 pairs, 10 and 19, 10 and 24, 19 and 24. Step 2, the greatest common divisor of 10 and 19 is 1. Fine so far. Step 3, now 10 and 24, both are even, so 2 divides both. Their greatest common divisor is 2, not 1. This pair fails. Step 4, one failing pair is enough to break the whole list. We can stop right there. So 10, 19, and 24 are not pairwise relatively prime. Remember the shape of this work. You must be ready to check every pair, but you may stop the moment one pair fails. We will use this idea later when we solve systems of congruences. One way to find the greatest common divisor of two numbers starts from their prime factorizations. For a take prime p1 to the power of 1 times prime p2 to the power of 2 and so on. Do the same for b. Use the same list of primes for both, and if a prime is missing from one of them, give it the exponent 0. Now for each prime, take the smaller of the two exponents. The word min means the smaller one. Multiply those together, and you have the greatest common divisor. Set it up. 120 is 2 cubed times 3 times 5. 500 is 2 squared times 5 cubed. The primes in play are 2, 3, and 5. Line 0. We want the greatest common divisor of 120 and 500. Step 1. For each prime, take the smaller exponent. For 2, the exponents are 3 and 2. For 3, they are 1 and 0. For 5, they are 1 and 3. Step 2. Take the smaller each time. 2 squared, 3 to the 0, 5 to the first. The 3 vanishes because 500 has no factor of 3 at all. Step 3. Multiply out. 4 times 1 times 5 is 20, so the greatest common divisor is 20. But be careful. This method is slow, and the slow part is not the formula. The formula is easy. The trouble is the very first step, finding the prime factorization of a big number. Nobody knows a fast way to do that. In fact, the whole safety of RS rests on it being hard. So we need a method for the greatest common divisor that never factors anything at all. The Euclidean algorithm is exactly that method, and we meet it in a few slides. The least common multiple of NB is the smallest positive number that both A and B divide into evenly. We write it as LCM of NB. We can find it from the prime factorizations too. but this time we take the larger of the two exponents. The word max means the larger one. That makes sense. To be a multiple of A, you need at least as many copies of each prime as A has. Same for B, so you take whichever demand is bigger. Set it up. The first number is 2 cubed times 3 to the 5th times 7 squared. The second is 2 to the 4th times 3 cubed. The primes in play are 2, 3, and 7. Line 0. We want the least common multiple of those two numbers. Step 1. For each prime, take the larger exponent. For 2, the exponents are 3 and 4. For 3, they are 5 and 3. For 7, they are 2 and 0, since the second number has no 7 at all. Step 2. Take the larger each time. 2 to the 4th, 3 to the 5th, 7 squared. That is the least common multiple. There is a lovely link between the two ideas. Theorem 5 says that A times B equals the greatest common divisor of A and B times the least common multiple of A and B. So if you know one of them, division gives you the other. And this is why it makes sense. Look at any one prime. The greatest common divisor uses the smaller exponent. The least common multiple uses the larger one. The smaller and the larger are just the two original exponents in some order. So when you add them, you get exactly the exponent in A times B. The Euclidean algorithm is a fast way to find the greatest common divisor. Its great virtue is that it never factors anything. It only divides. This is the one fact behind it. Take two numbers A and B, with a bigger. Divide A by B and call the remainder C, then the greatest common divisor of A and B is the same as the greatest common divisor of B and C. The pair shrinks, but the answer does not change. So we keep dividing and keep replacing until the numbers are small enough to read the answer off. Set it up. Put the larger number first. So A is 287 and B is 91. Now divide, keep the remainder, and repeat. Round 1. Divide 287 by 91. 91 times 3 is 273, and the remainder is 14. Round 2. The old divisor becomes the new dividend, and the remainder becomes the new divisor. So divide 91 by 14. 14 times 6 is 84, and the remainder is 7. Round 3. Divide 14 by 7. 7 times 2 is 14 exactly, so the remainder is 0. We stop. Now watch the same run written as a chain of greatest common divisors. Line 0. We start at the greatest common divisor of 287 and 91. Step 1. The first division gave remainder 14, so the pair becomes 91 and 14, and the answer is unchanged. Step 2. The second division gave remainder 7, so the pair becomes 14 and 7. Step 3. The third division gave remainder 0, so the pair becomes 7 and 0. Step 4. The greatest common divisor of 7 and 0 is 7, because everything divides 0. So the answer is 7, which is the last non-zero remainder in the run. This is the same algorithm written as pseudocode. We start with x equal to A, and y equal to B, then we loop while y is not 0. Inside the loop, we set r to x mod y, which is the remainder when x is divided by y, then we shift down. X takes the old value of y, and y takes the value of r. We repeat until y becomes 0, and then we return x. This method is very fast. The running time is big O of log b, where O is larger than b. Even for huge numbers, it finishes in very few steps. Why does the Euclidean algorithm work? Lemma 1 gives the reason. Suppose A equals B times Q plus R. In other words, R is the remainder when A is divided by B. We also ask that A and B are not both 0. The lemma says the greatest common divisor of A and B is the same as the greatest common divisor of B and R. Set it up carefully. To prove that, we show something stronger. The pair A and B and the pair B and R have exactly the same common divisors. If the two sets of common divisors match, then their largest members match too. Now the working, one direction at a time. Step 1. Take any number D that divides both A and B, then D also divides A minus B times Q, and by our equation, that difference is exactly R, so D divides B and R as well. Step 2. Now go the other way. Take any D that divides both B and R, then D divides B times Q, plus R, and that sum is exactly A, so D divides A and B as well. Step 3. Both directions hold, so the two pairs have exactly the same common divisors. Step 4. If the sets of common divisors are the same, their largest members are the same. So the greatest common divisor of A and B equals the greatest common divisor of B and R, that is lemma 1. Now let's see why the algorithm always stops. Start with A at least as big as B call of the value R0, and call B the value R1. Line 0, the first division. R0 equals R1 times Q1 plus R2, and R2 is at least 0 and smaller than R1. Step 1, the next division. R1 equals R2 times Q2 plus R3. Again, the new remainder is smaller. Step 2, and so on. Every division makes the remainder strictly smaller than the one before. Step 3, keep going down the chain. Step 4, eventually a remainder is 0 and the run stops. Why must it? Because the remainders keep shrinking but stay at least 0, and whole numbers cannot shrink forever. Let's put the two pieces together. From R1 onward, every remainder is strictly smaller than the one before, and none of them ever goes below 0. Whole numbers cannot keep falling forever, so sooner or later a remainder hits 0 and the run stops. Now apply lemma 1 to every step of the chain. Each division leaves the greatest common divisor unchanged. So the greatest common divisor of A and B equals the greatest common divisor of R sub n and 0. And that is just R sub n. So this is the rule to remember. The greatest common divisor is the last non-zero remainder in the run. This is a beautiful fact, named after the French mathematician Étienne Bezel. Take any two positive integers A and B. Then you can always find two integers s and t, so that the greatest common divisor of A and B equals s times A plus t times B. The two integers s and t are called the Bezout coefficients. The equation itself is called Bezout's identity. Notice that s and t may be negative, and usually one of them is. The proof is in the exercises of section 5.2. A sum like s times A plus t times B is called a linear combination of A and B. Bezout's theorem says the greatest common divisor is always one of these combinations. Line 0, take 6 and 14. Their greatest common divisor is 2. Step 1, we can write 2 as minus 2 times 6 plus 1 times 14. So the Bezout coefficients here are minus 2 and 1. Notice that one of them is negative. That is normal. Step 2, always check. Minus 2 times 6 is minus 12. Plus 14 gives 2. It works. Let's express a greatest common divisor as a linear combination. Our numbers are 252 and 198, and we are told the answer is 18. Set it up first because the shape of the work matters. This is a two-pass method. On the forward pass, we run the Euclidean algorithm and write down every single division. On the backward pass, we start from the last useful division and substitute our way back up, one line at a time. Each substitution replaces a remainder by the two numbers that made it. This is the forward pass. Label each division because we will need them by name. Round 1. 252 equals 1 times 198 plus 54. Round 2. 198 equals 3 times 54 plus 36. Round 3. 54 equals 1 times 36 plus 18. Round 4. 36 equals 2 times 18 exactly, with nothing left over. So the run stops, and the last non-zero remainder is 18. That confirms the greatest common divisor is 18. Now the backward pass line by line. Line 0, we must express 18. Step 1. Rearrange division 3. 18 equals 54 minus 1 times 36. Step 2. Now get rid of the 36. Division 2 says 36 equals 198 minus 3 times 54. Substitute that in. Step 3. Collect the 54s. We had 154 and the substitution brought 3 more. So 4 times 54 minus 1 times 198. Step 4. Now get rid of the 54. Division 1 says 54 equals 252 minus 1 times 198. Substitute that in. Step 5. Collect again. We get 4 times 252 minus 5 times 198. So S is 4 and T is minus 5. Check it if you like. 1008 minus 990 is 18. Step back and look at the shape of what we did. It was a two-pass method. First, we ran the Euclidean algorithm forward all the way to the answer, writing down every division. Then we walked back up, substituting, until only the two original numbers were left. There is also a one-pass method called the extended Euclidean algorithm. It carries the coefficients along as it divides, so it never has to walk back. That is what a computer would use. The book develops it in the exercises. Bézout's theorem has useful consequences. Lemma 2 says this. Suppose A and B share no common factor, so their greatest common divisor is 1. And suppose A divides the product B times C, then A must divide C all by itself. Set it up. Because the greatest common divisor of A and B is 1, Bézout hands us two whole numbers S and T with S times A plus T times B equal to 1. That is the tool. What we must show is that A divides C. Now the working. Line 0. Bézout gives us S times A plus T times B equals 1. Step 1. Multiply both sides by C. Now S is C plus TBC equals C. Step 2. Look at the first term. S is C, it has an A in it, so it divides it. Step 3. Look at the second term. TBC, we were given that A divides BC in Theorem 1. Part 2 says that if A divides BC, then A divides T times BC, so A divides the second term too. Step 4. A divides both terms, so A divides their sum. And their sum is C, so A divides C, that proves lemma 2. Lemma 3 is about primes. If a prime P divides a long product, a 1 times a 2 up to a n, then P must divide at least one of the factors on its own. A prime cannot be spread thinly across several factors. It has to land whole inside one of them. The proof uses mathematical induction, which we meet in Chapter 5, so we leave it to exercise 64 there. But remember this lemma. It is the key to proving that prime factorization is unique, and that proof is next. Now we prove that a number has only one prime factorization once the primes are listed from small to large. This is the uniqueness half of the fundamental theorem of arithmetic. The existence half is proved in section 5.2. Set it up. We argue by contradiction. Suppose some positive integer n could be written as a product of primes in two genuinely different ways. Call the first way P1 times P2 up to PS. Call the second way Q1 times Q2 up to QT. Now the working. Step 1. Cancel every prime that appears in both lists. Whatever survives on the left equals whatever survives on the right. Step 2. And by construction, the two surviving lists share no prime at all. That is exactly what canceling did. Step 3. Now look at the first surviving prime on the left, P sub I1. It divides the left side and the two sides are equal, so it divides the right side too. Step 4. The right side is a product of primes. By lemma 3, P sub I1 must divide one of them, say Q sub jk, but Q sub jk is prime, and its only divisors are 1 and itself. So P sub I1 must equal Q sub jk. Step 5. That is a contradiction because we already canceled every shared prime, so the two factorizations were never really different. The prime factorization is unique. Earlier we saw that you cannot always divide both sides of a congruence by the same number. 14 congruent to 8, mod 6, broke when we divided by 2. Now we can say exactly when division is safe. Theorem 7. Suppose a times c is congruent to b times c, mod m, and suppose that c and the modulus m share no common factor, so their greatest common divisor is 1. Then you may cancel the c and conclude that it is congruent to b mod m. Look back at our broken example. Their c was 2 and m was 6, and 2 and 6 share the factor 2. That is why it failed. First clear two easy cases. If A already equals b, there is nothing to prove. And if the modulus m is 1, then every pair of integers is congruent, so again there is nothing to prove. So from here on, a minus b is not 0, and c is not 0 either. That matters, because lemma 2 is stated for positive integers. Now the working, and notice that lemma 2 does the real job. Line 0. We are given that a times c is congruent to b times c, mod m. Step 1. By the definition of congruence, m divides a c minus bc. Step 2. Factor out the c. Divisibility does not care about signs, so we may write this as m divides the size of c times the size of a minus b. Both of those are now positive whole numbers. Step 3. Now use lemma 2 with m playing the role of a and the size of c playing the role of b. Since m and c share no common factor, m must divide the other factor, the size of a minus b, on its own. And again signs do not matter, so m divides a minus b. Step 4. And that is exactly what it means to say it is congruent to b, mod m. Section 4.4. Solving congruences. So far we have learned how to add, multiply, and compare numbers using modular arithmetic. Now we turn to solving equations in this world. We will learn how to find the unknown x in a congruence, how to find an inverse of a number modulo m, and how to solve several congruences at once. Let's look at what this section covers. we start with linear congruences. These are equations with a mod on them. Then we meet the Chinese Remainder Theorem. It solves several congruences at the same time. We skip computer arithmetic with large integers here. You can read it in the book. Then comes Fermat's little theorem, a fast way to work with big powers. After that, pseudoprimes, which look prime but are not. And last, primitive roots and discrete logarithms. A linear congruence looks like this. A times x is congruent to b. Mod m here, m is a positive whole number. The letters a and b are whole numbers too, and x is what we want to find. A solution is any whole number x that makes the congruence true. Whenever x works, so does x plus m, and x plus 2m, and so on. So solutions always come in whole congruence classes. How many classes? That depends on a and m. When a and m share no common factor, there is exactly one class, and that is the case we spend most of our time on. But not always. 2x congruent to 3 mod 6 has no solution at all because the left side is always even. And 2x congruent to 2 mod 6 has two classes, x congruent to 1 and x congruent to 4. Now the key tool for solving these. An inverse of a mod m is a number we write as a bar. It has one job. A bar times a is congruent to 1. Mod m, think of it as the reciprocal, but for clock arithmetic. Why do we want it? Because to solve a times x is congruent to b, we cannot simply divide by a. Division is unsafe, as we saw. But we can multiply both sides by a bar, and that cancels the a on the left. Multiplying is always allowed. Let's check a claim. 5 is an inverse of 3 mod 7, line 0. The test is the product 5 times 3. Step 1, 5 times 3 is 15. Step 2, now divide by the modulus 7. 15 is 2 sevens, 14 plus 1. Step 3, so 15 is congruent to 1 mod 7. That is exactly the definition. So 5 is an inverse of 3 mod 7. When does an inverse exist? Theorem 1 gives the answer. If a and m share no common factor bigger than 1 and m is more than 1, then an inverse of a mod m exists. And it is unique, mod m. Remember what relatively prime means. The greatest common divisor of a and m is 1. So the whole existence question reduces to a greatest common divisor, and we already have a fast way to compute those, the Euclidean algorithm. That is a nice piece of luck, and it is not a coincidence. Bezout does the heavy lifting here. Line 0. Because the greatest common divisor of a and m is 1, Bezout's theorem hands us whole numbers s and t with s times a plus t times m equal to 1. Step 1. Now read that whole line mod m. Step 2. Look at the term t times m. It is a multiple of m, so it is congruent to 0. It drops out. Step 3. That leaves s times a congruent to 1, mod m, and that is exactly the definition of an inverse. So s is the inverse we wanted. Uniqueness is left as exercise 7. Let's find an inverse of 3, mod 7, using the method rather than by guessing. Step 1. Set it up. First check that an inverse exists. Is the greatest common divisor of 3 and 7 equal to 1? Yes, 7 is prime and does not divide 3. Step 2. Run the Euclidean algorithm on 7 and 3. 7 equals 2 times 3 plus 1. That is the whole run because the remainder is already 1. Step 3. Rearrange to make 1 the subject. 1 equals 7 minus 2 times 3. Step 4. Read off the Bezout coefficients. Minus 2 times 3 plus 1 times 7 equals 1. Step 5. The inverse is the coefficient sitting next to the 3, so 3 bar is minus 2. One more thing about inverses. They are not a single number. Every integer congruent to minus 2 mod 7 is also an inverse of 3 mod 7. So minus 2 works, and so do 5, minus 9, and 12. They are all the same thing seen from different places on the clock. In practice, we usually quote the one that sits inside the set 0 to m minus 1. Here that is 5. Check 2 of them. 5 times 3 is 15, which is congruent to 1 mod 7. 12 times 3 is 36, which is 35 plus 1, so also congruent to 1. Both work. Now a bigger example. We want an inverse of 101, mod 4620. Set it up. Step 1 is always the same. Check that the greatest common divisor is 1. Run the Euclidean algorithm, larger number first. Round 1. 4620 equals 45 times 101 plus 75. Round 2. 101 equals 1 times 75 plus 26. Round 3. 75 equals 2 times 26 plus 23. Round 4. 26 equals 1 times 23 plus 3. The numbers are shrinking fast. We carry on with the same 3 numbers rule. The old divisor becomes the new dividend, and the old remainder becomes the new divisor. Round 5. 23 equals 7 times 3 plus 2. Round 6. 3 equals 1 times 2 plus 1. Round 7. 2 equals 2 times 1 with nothing left over. The remainder is 0, so we stop here. Read off the answer. The last remainder that was not 0 is 1. So the greatest common divisor of 101 and 4620 is 1. The two numbers are relatively prime. By Theorem 1, that guarantees an inverse exists, but knowing it exists is not the same as having it. To find it, we work the divisions backwards, exactly the way we found Bezout coefficients earlier. That is the next slide. Now the backward pass. Each step replaces the newest remainder by the two numbers that made it, and then we collect terms. Line 0, we must express 1. Step 1, rearrange round 6. 1 equals 3 minus 1 times 2. Step 2, replace the 2 using round 5. Collect. We get minus 1 times 23 plus 8 times 3. Step 3, replace the 3 using round 4. Collect. We get 8 times 26 minus 9 times 23. Step 4, replace the 23 using round 3. Collect. We get 26 times 26 minus 9 times 75. Step 5, replace the 26 using round 2. Collect. We get 26 times 101 minus 35 times 75. Step 6, replace the 75 using round 1. Collect one last time. We get minus 35 times 4620 plus 1601 times 101. Now read off the inverse. The Bezout coefficients are minus 35 and 1601. Take that last line and read it modulo 4620. The first term is minus 35 times the modulus itself, so it vanishes. What is left is 1601 times 101, congruent to 1. That is the definition of an inverse. So 1601 is an inverse of 101, mod 4620. Now we use an inverse to solve a congruence. What are the solutions of 3x congruent to 4 mod 7? Set it up. The unknown is x. The modulus is 7. The coefficient we must remove is 3. And we already worked out that an inverse of 3 mod 7 is minus 2. Line 0. We are given 3x congruent to 4 mod 7. Step 1. Multiply both sides by minus 2. Multiplying is always safe. Step 2. Multiply out. Minus 6x is congruent to minus 8. Step 3. Now simplify both sides mod 7. Minus 6 is congruent to 1, so the left side becomes just x, and minus 8 is congruent to 6, so x is congruent to 6 mod 7. We should always check, because multiplying by an inverse only shows that any solution must look like this. It does not by itself show that every such x works. So assume x is congruent to 6 mod 7. Then by Theorem 5 of section 4.1, 3x is congruent to 3 times 6, which is 18. And 18 is congruent to 4 mod 7 because 18 minus 4 is 14. That is what we wanted, so every such x really does solve it. The full answer is the whole class. 6, 13, 20, and going the other way, minus 1, minus 8, minus 15, and so on forever. This is an old puzzle. Almost 2,000 years ago, a Chinese mathematician named Sun-Tsu asked it. We have some things, and we do not know how many. When we count them off in groups of 3, 2 are left over. In groups of 5, 3 are left over. In groups of 7, 2 are left over. How many things are there? It sounds like a riddle, but it is exactly a modular arithmetic problem. This is the puzzle written in symbols. X is congruent to 2 mod 3. X is congruent to 3 mod 5. X is congruent to 2 mod 7. The word and matters here. We do not want a number that satisfies one of these. We want a single x that satisfies all 3 at the same time. A set of congruences like this is called a system, and the theorem that solves such systems is called the Chinese Remainder Theorem, named after this very puzzle. Now the theorem itself. Take several moduli, m1, m2, up to m, and they must be pairwise relatively prime. That means any two of them share no common factor bigger than 1. Then pick any target remainders you like, a 1, a 2, up to a n. The theorem says the whole system has a unique solution, modulo big M, where big M is all the moduli multiplied together. Let's be careful about what unique means here. It does not mean there is only one number. It means there is exactly one answer in the window from 0 up to big M minus 1. Every other answer is that 1, plus a whole number of big M steps. The book leaves uniqueness as exercise 30. Existence is the interesting half, and we prove it by actually building the solution. That is the best kind of proof, because it hands you a method as well as a fact. This is how we build the answer. There are 4 pieces. 1. Multiply all the moduli together and call the result big M. 2. For each modulus m sub k, form big M sub k by dividing big M by M sub k, so big M sub k is the product of all the other moduli, leaving M sub k out. 3. Now, big M sub k and M sub k share no common factor. Why? Because the moduli are pairwise relatively prime, so none of the others shares anything with M sub k. 4. Since they are relatively prime, Theorem 1 guarantees an inverse. Call it y sub k, so big M sub k times y sub k is congruent to 1, mod M sub k. Now form the sum. take a 1 times big M 1 times y1 plus a 2 times big M 2 times y2 and so on. Call the whole sum x. Now check it works. Line 0. Look at x modulo one particular m sub k. Step 1. Every term except the kth1 contains m sub k inside its big M, so every one of them is congruent to 0. Only the kth term survives. Step 2. And in that term, big M sub k times y sub k is congruent to 1. By the way, we chose y sub k, so the term is a sub k times 1. Step 3. So x is congruent to a sub k, mod m sub k, and that holds for every k, so x solves the whole system at once. Let's do Sun-Tsu's numbers one step at a time. Set it up. The moduli are 3, 5, and 7. The targets are 2, 3, and 2. Step 1. First check the theorem applies. Are the moduli pairwise relatively prime? Yes. They are 3 different primes, so no 2 of them share a factor. Step 2. Multiply them. Big M is 3 times 5 times 7, which is 105. Step 3. Big M1 is 105 divided by 3, which is 35. Step 4. Big M2 is 105 divided by 5, which is 21. Step 5. Big M3 is 105 divided by 7, which is 15. Next, we need the 3 inverses. A good habit is to reduce each big M first, then find the inverse of the small number. 1. We want the inverse of 35 mod 3. 35 mod 3 is 2, and 2 times 2 is 4, which is congruent to 1 mod 3, so y1 is 2. 2. We want the inverse of 21 mod 5. 21 mod 5 is 1, and 1 is its own inverse, so y2 is 1. 3. We want the inverse of 15 mod 7. 15 mod 7 is 1, so y3 is 1 as well. Notice how reducing first made all 3 easy. Never work with the big number when a small one will do. Now put it together. Line 0. The construction says x is a 1 times big M1 times y1 plus the same shape for the other 2. Step 1. Put in the numbers. 2 times 35 times 2 plus 3 times 21 times 1 plus 2 times 15 times 1. Step 2. Work out each term. 140 plus 63 plus 30. Step 3. Add them. 233. Step 4. Finally reduce mod 105. 233 minus 2 times 105 is 23, so x is congruent to 23. Always check. Sun-Tsu asked 3 questions, so we answer all 3. 1. 23 divided by 3. 3 sevens is 21, so the remainder is 2. That matches. 2. 23 divided by 5. 4 fives is 20, so the remainder is 3. That matches. 3. 23 divided by 7. 3 sevens is 21, so the remainder is 2. That matches too. So 23 is the smallest positive number of things that fits Sun-Tsu's description. And so is 23 plus 105, and so on. There is a second method, and some people find it easier, because it handles one congruence at a time instead of building one big sum. It is called back substitution. It still needs an inverse now and then, as we will see. Step 1. Take the first congruence and rewrite it as an ordinary equation, using Theorem 4 of Section 4.1. Step 2. Put that expression into the next congruence, and solve for the new variable that appeared. Step 3. Repeat until every congruence has been used. At the end you have one equation, and you turn it back into a congruence. Let's work 1. We want all integers x with x congruent to 1 mod 5, x congruent to 2 mod 6, and x congruent to 3 mod 7. Set it up. First check the moduli. 5, 6, and 7 are pairwise relatively prime. 5 and 6 share nothing, 6 and 7 share nothing, 5 and 7 share nothing. So a solution exists, unique mod 5 times 6 times 7, which is 210. Now take the first congruence. X is congruent to 1 mod 5. By Theorem 4, we may write it as an equation. X equals 5t plus 1, where t is some whole number. Now use the second congruence. Line 0. Put x equals 5t plus 1 into x congruent to 2 mod 6. That gives 5t plus 1 congruent to 2 mod 6. Step 1. Solve for t. 5t is congruent to 1 mod 6, and 5 times 5 is 25, which is congruent to 1. So t is congruent to 5 mod 6. Step 2. Use Theorem 4 again. T equals 6u plus 5, where u is a whole number. Step 3. Put that back into x equals 5 times 6u plus 5 plus 1. Multiply out 30u plus 25 plus 1, which is 30u plus 26. Now the third congruence and the same moves again. Line 0. Put x equals 30u plus 26 into x congruent to 3 mod 7. Step 1. Reduce mod 7. 30 is congruent to 2 and 26 is congruent to 5. So 2u plus 5 is congruent to 3. Solving gives u congruent to 6 mod 7. Step 2. Theorem 4 once more. U equals 7v plus 6. Step 3. Put that back into x equals 30 times 7v plus 6 plus 26. That is 210v plus 180 plus 26, which is 210v plus 206. Step 4. Turn it back into a congruence. X is congruent to 206 mod 210. Notice the modulus is the product of all three, exactly as the theorem promised. Now a very handy shortcut, from Pierre de Fermat, a French lawyer who did mathematics in his spare time and changed the subject forever. Fermat's little theorem says this: if p is a prime and it is not a multiple of p, then a raised to the power p minus 1 is congruent to 1. Mod p, there is also a second form that needs no condition at all. For every integer a to the power p is congruent to a mod p. It is called little to tell it apart from Fermat's last theorem, which is a different and much harder story. Why is this useful? Because it kills huge exponents. Once you know that a to the power p minus 1 is congruent to 1, then any whole multiple of that exponent is also congruent to 1. 1 raised to any power is still 1. So when you meet a giant exponent, you split it. Take out as many copies of p minus 1 as you can. Those all collapse to 1. What is left is just the remainder, and that is small. A power with hundreds of digits in the exponent becomes a power you can do by hand. Set it up. Here p is 11 and it is 7. 11 does not divide 7, so Fermat applies. That gives us 7 to the 10th is congruent to 1 mod 11. Line 0. We want 7 to the 222nd power. Step 1. Split the exponent using 10, which is p minus 1. 222 is 22 times 10 plus 2. Step 2. By the law of exponents, that is 7 to the 10th, all raised to the 22nd times 7 squared. Step 3. Now Fermat kills the big part. 7 to the 10th is congruent to 1, and 1 to any power is 1. So all that remains is 7 squared, which is 49. Step 4. Reduce 49 mod 11. 49 is 4 11s, 44 plus 5. So the answer is 5. Fermat's little theorem gives us a test, but it only works in one direction. If n is a prime bigger than 2, then 2 to the power n minus 1 is congruent to 1. Mod n that much is guaranteed. Now turn it around. Suppose we compute 2 to the power n minus 1 and get 1. Does that make n prime? No. Some composite numbers pass the test anyway. We call such a number a pseudoprime to the base 2. Pseudo means false. It is a fake prime, one that fools this particular test. This is the classic example worked through. Step 1. Is 341 composite? Try the small primes. 11 divides it. 341 is 11 times 31. So yes, it is composite. Step 2. Now the lucky break. 2 to the 10th is 1024, and 1024 is 3 times 341 plus 1. So 2 to the 10th is congruent to 1, mod 341. Step 3. Now look at the exponent we need. 340 is 10 times 34, so 2 to the 340th is 2 to the 10th, all raised to the 34th, and 1 raised to anything is still 1. Step 4. So this is a composite number that passes the primality test. 341 is a pseudoprime to the base 2. We are not stuck with base 2. We can run the same test with any base b at least 2. If n is composite and b to the power n minus 1 is congruent to 1, mod n, we say n is a pseudoprime to the base b. And this is the practical value. A number that fools base 2 may well fail base 3. So we test with several bases. Each extra test that passes makes it more likely that n really is prime. Take any integer n bigger than 2, which is what Fermat's little theorem needs. The test then works like a filter with 2 outcomes. 1. If the congruence fails, we are done. The number n is composite, and we are certain of it, and we learned this without finding a single factor. 2. If the congruence holds, we are not finished. The number n is either a real prime or a pseudoprime. And this is the good news. Pseudoprimes are very rare. Below 10 to the power 10, there are more than 455 million primes, but fewer than 15,000 pseudoprimes to the base 2. So passing a few tests is strong evidence. Let's meet a new idea, the primitive root. Take a prime p and look at z sub p, the numbers from 0 up to p minus 1. A primitive root is a special number r. When we raise r to the powers 1, 2, 3, and so on, mod p, we hit every non-zero value before anything repeats. So a primitive root is a generator. Its powers sweep through the whole set. That makes it a natural base for exponents, and we will use exactly that in the next few slides and again in cryptography. Let's test the number 2 with the prime 11. Walk along the bottom row. 2 to the first is 2, 2 squared is 4, 2 cubed is 8, 2 to the fourth is 16, which is 5 mod 11, 2 to the fifth is 10, 2 to the sixth is 9, 2 to the seventh is 7, 2 to the eighth is 3, 2 to the ninth is 6, and 2 to the 10th is 1. Now look at what we collected. 2, 4, 8, 5, 10, 9, 7, 3, 6, 1. That is all 10 non-zero values, each exactly once. So 2 is a primitive root of 11. Now try 3 with the same prime 11. 3 to the first is 3, 3 squared is 9. 3 cubed is 27, which is 5 mod 11. 3 to the 4th is 15, which is 4. And 3 to the 5th is 12, which is 1. We are back at 1 after only 5 steps. Once you hit 1, the whole pattern starts again. So the powers of 3 only reach 5 values: 3, 9, 5, 4, and 1. They miss the other 5. So 3 is not a primitive root of 11. The good news is that every prime has at least one primitive root. You may have to hunt, but one is always there. Now let's reverse the primitive root idea. Take a prime P and a primitive root R, because the powers of R sweep through every non-zero value exactly once. Each target value is hit by exactly one exponent. That exponent gets a name. We call it the discrete logarithm of a modulo P to the base R, and we write it like an ordinary logarithm. Log base R of a equals E, it behaves much like the logarithm you already know, except that we are working on a clock instead of on the number line. Set it up. Our prime is 11 and our base is 2. We already checked that 2 is a primitive root of 11, so every non-zero value has exactly one logarithm. Question 1. Which power of 2 gives 3? Look back at the table of powers. 2 to the 8th is 3 mod 11, so the discrete logarithm of 3 to the base 2 is 8. Question 2. Which power of 2 gives 5? 2 to the 4th is 5 mod 11, so the discrete logarithm of 5 to the base 2 is 4. Notice how we answered by reading a table. That is the honest way, and it is also the problem. This is the key point, and it is the whole reason we care. Going forward is easy. Give me an exponent e, and modular exponentiation gives me a quickly, even for enormous numbers. Going backward is hard. Give me a value a and ask which exponent produced it, and nobody knows a fast method for an ordinary computer. For a small prime like 11, we just read the table. For a prime with hundreds of digits, no table can be built and no shortcut is known. One honest footnote: a large quantum computer could do it using Shor's algorithm. Nobody has built one big enough yet, and that is why researchers are already designing ciphers meant to survive one. That gap between easy forward and hard backward is exactly what cryptography needs, and it is what we use in section 4.6. Section 4.5, Applications of Congruences. Number theory is not only beautiful, it is also useful. In this section we see 3 real uses of modular arithmetic: hashing functions, pseudorandom numbers, and check digits. This is our plan for this section. 3 topics, and all 3 use the mod function. Hashing functions help us store and find records quickly. Pseudorandom numbers let a computer act as if it is rolling dice. And check digits let us spot mistakes in strings of digits, like product bar codes and book numbers. Let's start with hashing. Imagine a huge set of records, and we must decide where to keep each one in memory. A hashing function makes that decision. It takes the key of a record and hands back a memory location. A common choice is h of k equals k mod m, where m is the number of available locations. This squeezes any key, however large, into the range 0 to m minus 1. And because the mod function is onto, every location can be reached. No memory sits unused. Set it up. Our keys are social security numbers. We have 111 locations, numbered 0 to 110. So the hashing function is k mod 111. Key 1. 064212848 mod 111 gives 14. Location 14 is free, so the record goes there. Key 2, 037149212 gives 65. That location is free too. Key 3, 1074057723 also gives 14, but location 14 is already occupied. Two different keys want the same slot. Now what? That clash has a name. It is called a collision. Collisions are unavoidable. Hashing cannot be one-to-one because there are far more possible keys than there are locations. 9-digit social security numbers give a billion possible keys, and we only have 111 boxes. So many keys must share. So a collision is not a bug in your program. It is a fact of life, and every hashing scheme needs a rule for handling one. This is the simplest rule, called linear probing. We compute h of k plus I, all mod m, trying I equal to 0 first, then 1, then 2, and so on, until we find a free spot. The mod m at the end makes the search wrap around the end of the table back to the start. In our example, key 3 hashed to 14, and 14 was taken. So we try I equal to 1, which gives 15. That location is free, so the record goes there. Many other collision methods exist, and you will meet them in a later computer science course. Next, pseudorandom numbers. Many programs need random numbers, for example, to run a simulation of traffic or of a queue at a bank. But an ordinary computer cannot really be random. It follows instructions. So instead it follows a fixed recipe that only looks random. We call the output pseudorandom, meaning false random. One common recipe is the linear congruential method. It needs 4 whole numbers: the modulus m, the multiplier the increment c, and the starting value called the seed x0. Each has a range shown here. This is the whole recipe in one line. To get the next number, take a times the current number, add c, and then take the result mod m. First, every output stays between 0 and m minus 1 because of the mod. It never escapes the range. Second, if you want numbers between 0 and 1, as most simulations do, just divide each output by the modulus m. Let's work an example. We choose modulus 9, multiplier 7, increment 4, and seed 3. So the rule becomes x sub n plus 1 equals 7 times x sub n plus 4 mod 9. We start with x0 equal to 3. Step 1. 7 times 3 is 21, plus 4 is 25. 25 mod 9 is 7, because 18 leaves 7. Step 2. 7 times 7 is 49, plus 4 is 53. 53 mod 9 is 8. Step 3. 7 times 8 is 56, plus 4 is 60. 60 mod 9 is 6. Step 4. 7 times 6 is 42, plus 4 is 46. 46 mod 9 is 1. We keep going with the same rule. Step 5. 7 times 1 is 7, plus 4 is 11. 11 mod 9 is 2. Step 6. 7 times 2 is 14, plus 4 is 18. 18 mod 9 is 0 exactly. Step 7. 7 times 0 is 0, plus 4 is 4. 4 mod 9 is 4. Step 8. 7 times 4 is 28, plus 4 is 32. 32 mod 9 is 5. Step 9. 7 times 5 is 35, plus 4 is 39. 39 mod 9 is 3, and 3 is our seed, so the sequence has come all the way around. This is the whole sequence: 3, 7, 8, 6, 1, 2, 0, 4, 5, and then 3 again, and off it goes. It repeats after 9 terms. That is not a surprise. There are only 9 possible values, so a repeat must happen within 9 steps. And once one value comes back, the whole pattern must come back with it, because each term depends only on the term before it. The length before repeating is called the period. A good generator has a very long period. Our little example had a period of 9, which is useless in practice. Real generators use much larger parameters. When the increment c is 0, we call it a pure multiplicative generator. A well-known one uses the modulus 2 to the 31 minus 1 and the multiplier 7 to the 5th, which is 16,807. That combination runs for 2 to the 31 minus 2 numbers before repeating. That is over 2 billion values. One catch: the seed must not be 0. With a 0 seed, the rule just multiplies 0 by the multiplier, so it returns 0 forever. Now check digits. This is a clever trick to catch typing mistakes. We add one extra digit to the end of a number. It is not new information. It is chosen so that a certain weighted sum comes out to 0, modulo 10 or modulo 11. Now suppose somebody mistyped one digit. The weighted sum changes, so it is no longer 0, and the machine knows something is wrong. It cannot always tell you what is wrong, but knowing there is an error is already worth a lot. Take the universal product code, the bar code printed on shop items. It has 12 digits, and the last one is the check digit. The rule is a weighted sum. Multiply the digits in the odd positions by 3. Take the digits in the even positions as they are. Add everything up. The total must be congruent to 0 mod 10. The 3 is there on purpose. Weighting alternate digits differently is what lets the code catch a swap of 2 neighboring digits, not just a single wrong digit. Let's find the check digit, step by step. The first 11 digits are 7, 9, 3, 5, 7, 3, 4, 3, 1, 0, 4. Line 0. Start with the first 6 positions. Odd positions get a 3 in front. So 3 times 7 plus 9 plus 3 times 3 plus 5 plus 3 times 7 plus 3. Step 1, work them out. 21, 9, 9, 5, 21, 3. That adds to 68. Step 2. Now position 7 to 11. 3 times 4 plus 3 plus 3 times 1 plus 0 plus 3 times 4. Step 3, work them out. 12, 3, 3, 0, 12. That adds to 30. Step 4, add the 2 halves. 68 plus 30 is 98. That is the known part of the weighted sum. Now solve for the missing digit. Line 0. The rule says the whole weighted sum must be congruent to 0 mod 10. So 98 plus the check digit is congruent to 0. Step 1. Reduce the 98 first. 98 is congruent to 8 mod 10. So 8 plus the check digit is congruent to 0. Step 2. What must we add to 8 to reach a multiple of 10? 2. So the check digit is 2. Check it. 98 plus 2 is 100, and 100 is a multiple of 10. It works. Now let's check a whole code. Set it up. This time all 12 digits are present, including the check digit. So we apply the same weighted sum to all of them, and we hope for 0. Line 0. First 6 positions. 3 times 0 plus 4 plus 3 times 1 plus 3 plus 3 times 3 plus 1. Step 1, work them out. 0, 4, 3, 3, 9, 1. That adds to 20. Step 2, last 6 positions. 3 times 0 plus 2 plus 3 times 1 plus 6 plus 3 times 4 plus 1. Step 3, work them out. 0, 2, 3, 6, 12, 1. That adds to 24. Step 4, add the halves. 20 plus 24 is 44. Now the verdict, line 0. Our weighted sum is 44. Step 1, reduce mod 10. 44 is 4 tens plus 4, so it is congruent to 4. Step 2, 4 is not 0. The test fails. So this string is not a valid universal product code. Somewhere a digit is wrong. And notice what the test does and does not tell us. It says there is an error. It does not say which digit, and it does not say what the right code was. Books have their own code. The 10-digit ISB and the first 9 digits name the language, the publisher, and the title. The 10th digit is the check digit. The rule uses position weights. Multiply each digit by its position, 1 through 9, add them up, and take the result mod 11. That gives the check digit. The second line says the same thing another way. With all 10 terms included, the weighted sum must be congruent to 0. Notice the modulus. It is 11, and 11 is prime. That choice makes the test stronger, as we will see at the end. Let's find an ISBN check digit. The 9 digits are 0, 0, 7, 2, 8, 8, 0, 0, 8. Line 0, take positions 1 to 5. Multiply each digit by its position. 1 times 0, 2 times 0, 3 times 7, 4 times 2, 5 times 8. Step 1, work them out. 0, 0, 21, 8, 40. That adds to 69. Step 2, now position 6 to 9. 6 times 8, 7 times 0, 8 times 0, 9 times 8. Step 3, work them out. 48, 0, 0, 72. That adds to 120. Step 4, add the two halves. 69 plus 120 is 189. Now reduce. Line 0. The rule says the check digit is congruent to 189, mod 11. Step 1. How many 11s fit in 189? 17 of them make 187. Step 2, so the remainder is 2. The check digit is 2. One more thing, and it explains a puzzle you may have seen on the back of a book. Because we work mod 11, the check digit can come out as 10. But 10 is not a single digit, so the standard writes the letter X for it. That is why some ISBNs end in an X. Now validate a full ISBN, set it up. The last symbol is X, which stands for 10. So the last term is 10 times 10. And the test is whether the whole weighted sum is congruent to 0, mod 11. Line 0. Positions 1 to 5. 1 times 0, 2 times 8, 3 times 4, 4 times 9, 5 times 3. Step 1, work them out. 0, 16, 12, 36, 15. That adds to 79. Step 2, position 6 to 10. 6 times 0, 7 times 1, 8 times 4, 9 times 9, and 10 times 10. Step 3, work them out. 0, 7, 32, 81, 100. That adds to 220. Step 4, add the halves. 79 plus 220 is 299. Now the verdict, line 0. Our weighted sum is 299. Step 1, divide by 11. 27 11s make 297, and 2 are left over. Step 2, 2 is not 0, the test fails. So this string is not a valid ISBN 10. If you typed it into a library system, it would refuse it, and it would be right too. Let's finish with why this design is so good. The ISBN check catches any single error. Change one digit and the weighted sum changes, so the test notices. It also catches any transposition error, which is when two digits get swapped by accident. That is a very common human mistake, and simpler schemes miss it. Both properties come from the modulus being 11, a prime. When you work mod a prime, a product can only be 0 if one of its factors is 0. So a small change in a digit can never be cancelled out by the weight. That is why book numbers use 11, and it is a lovely piece of applied number theory. Section 4.6, Cryptography. Cryptography is the science of secret messages. We take a plain message and change it so that only the right person can read it. Encryption means hiding a message. Decryption means getting it back. And we will use the modular arithmetic we learned earlier. This is our plan for this section. First, we look at classical cryptography, the old secret codes. Then we define a cryptosystem in a general way. Next, we meet public key cryptography, a modern idea where the locking key can be public. We study the RSA cryptosystem, which is used all over the internet today. We finish with cryptographic protocols, including key exchange and digital signatures. And primitive roots and discrete logarithms come back too, because the key exchange protocol rests on them. This is the Caesar cipher, named after Julius Caesar, who used it for military messages. The idea is simple. Shift every letter 3 steps forward in the alphabet, so B becomes E and X becomes A, because we run off the end and wrap around to the start. Making a message secret this way is called encryption. It is one of the oldest recorded ciphers, and it is a good place to start, because the mathematics is small enough to see all at once. This is how we do it with mathematics, in 3 steps. Step 1. Turn each letter into a number. A is 0, B is 1, and so on up to Z, which is 25. That set of numbers, 0 to 25, is called Z sub 26. Step 2. Apply the encryption function to each number. Step 3. Turn each number back into a letter. And this is the function. F of P equals, in brackets, P plus 3 mod 26. It adds 3 and then wraps around at 26. The mod is what makes the wrap happen. Let's encrypt the first 2 words, meet you. Read the table down each column. The top row holds the plain letters. The second row turns each letter into a number. M is 12, E is 4, T is 19, Y is 24, O is 14, and U is 20. The third row adds 3 to each one. 12 becomes 15, 4 becomes 7, 19 becomes 22, 14 becomes 17, 20 becomes 23. The last row turns the numbers back into letters. So we get P, H, H, W, then B, R, X. Now watch Y carefully. Y is 24. 24 plus 3 is 27, but 27 is too big, so we wrap. 27 mod 26 is 1, and 1 is the letter B. Now the rest of the message in the park. The numbers are 8, 13, 19, 7, 4, 15, 0, 17, 10. Add 3 to each one. We get 11, 16, 22, 10, 7, 18, 3, 20, 13. As letters, that is LQ, then WKH, then SDUN. Put the 2 halves together. Meet U in the park becomes PHHW, BRX, LQ, WKH, SDUN. To read a Caesar message, we do the reverse. We shift each letter back by 3. If a letter falls off the front of the alphabet, we wrap around to the end. So it goes back to X. Getting the message back is called decryption. The decryption function is f inverse of p equals, in brackets, p minus 3, mod 26. Notice that encryption and decryption are the same shape of operation. One adds, the other subtracts. That is a hint that the Caesar cipher is not very strong. Now a bigger idea. 3 was just one choice. We can shift by any number k. This whole family is called shift ciphers. To lock the message, add k and take mod 26. To unlock it, subtract k and take mod 26. The number k is the secret. We call it the key. If you know the key, you can read the message. If you do not, it is hidden. But notice there are only 26 possible keys, so a patient person could simply try them all. That is a serious weakness, and we come back to it. Let's try a shift cipher with key 11. Our message is stop global warming, and we take the first two words here. The numbers are 18, 19, 14, 15, then 6, 11, 14, 1, 0, 11. Add 11 to each one and wrap at 26. 18 plus 11 is 29, which wraps to 3. 19 gives 4. 14 gives 25. 15 plus 11 is 26, which wraps to 0. As letters, stop global becomes DEZA, RWZMLW. Now the last word, WRMING. The numbers are 22, 0, 17, 12, 8, 13, 6. Add 11 to each one. 22 plus 11 is 33, which wraps to 7. 17 plus 11 is 28, which wraps to 2. The rest need no wrap. As letters, that is H, L, C, X, T, Y, R. So the whole ciphertext is DEZA. RWZMLW, HLCXTYR. Notice how completely a small key hides the words. Now let's decrypt a message. We are told the key is 7, so we shift back by 7. The first cipher word is LEWLYPLUJL. As numbers, 11, 4, 22, 11, 24, 15, 11, 29, 11. Subtract 7 from each one. 11 gives 4. 4 minus 7 is minus 3, which is below 0, so we wrap around to 23. The rest come down cleanly. As letters, the first word is experience. Now the middle of the message. PZ, then H, then NYLH. As numbers, 15, 25, 7, 13, 24, 11, 7, 0. Subtract 7 from each one. 15 gives 8, 25 gives 18, 7 gives 0, and 0 minus 7 wraps around to 19. As letters, we get is a great. And the last word, a LHJOLY. As numbers, 0, 11, 7, 9, 14, 11, 24. Subtract 7 from each one. 0 wraps to 19. The others give 4, 0, 2, 7, 4, 17. That spells teacher. Put the whole thing together, and the hidden message is experience is a great teacher. A great teacher indeed. The affine cipher is a bigger family. Shift ciphers are a special case of it. Its function is f of p equals, in brackets, a times p plus b, mod 26. But there is a condition. For the cipher to be usable, f must be a bijection. That means every letter maps to a different letter and nothing is lost. Otherwise, two plain letters would encrypt to the same cipher letter, and no one could decrypt. That happens exactly when the greatest common divisor of N26 is 1. take a equal to 1, and you get back the shift cipher. So this really is a generalization. Set it up. Here A is 7 and B is 3. First check the condition. The greatest common divisor of 7 and 26 is 1, since 26 is 2 times 13 and 7 divides neither. So this is a valid affine cipher, and the letter K is number 10. Line 0, we want f of 10. Step 1, put in the numbers. 7 times 10 plus 3 all mod 26. Step 2, 7 times 10 is 70, plus 3 is 73. Step 3, now reduce. 73 is 2 26's 52 plus 21. So the answer is 21, and 21 is the letter V, so K becomes V. To decrypt, we solve for P line 0. Encryption says the cipher number C is congruent to a times P plus B, mod 26. Step 1. Subtract B from both sides. Adding and subtracting are always safe. Now C minus B is congruent to a times P. Step 2. Multiply both sides by a bar, the inverse of a modulo 26. Multiplying is safe too. Step 3. On the right, a bar times it is congruent to 1, so it cancels and leaves P alone. So P is congruent to a bar times, in brackets, C minus B. And notice why the inverse exists at all. Because the greatest common divisor of A and 26 is 1. That is the very same condition that made F a bijection. The two facts are really one fact. Cryptanalysis means breaking a code. We try to read a secret message without being told the key. A key tool is a simple fact about English. Some letters appear far more often than others. The letter E is the most common, about 13% of all letters. Then come T, A, O, I, N, S, H, and R. A shift cipher moves every letter by the same amount, so it moves the whole frequency pattern along without changing its shape. That is the weakness we attack. This is the plan in 4 steps. Step 1. Count the letters in the secret message and find the one that appears most often. Step 2. Guess that this letter came from E, since E is the most common letter in English. The gap from E to that letter tells us the key K. Step 3. Shift the whole message back by minus K and read the result. Step 4. If it reads like English, we win. If it is nonsense, our guess was wrong. Try the next most common letter T and go round again. It rarely takes many tries. Let's break a real one. Step 1. Set it up. We intercepted the message ZNK, KGXRE, HOXJ, MKZY, ZNK, CUXS. Count the letters. K appears most often 4 times. Step 2. Guess that K came from E. E is number 4, and K is number 10. So the shift is 10 minus 4, which is 6. Step 3. Now shift the whole message back by 6, letter by letter. Z becomes T, N becomes H, K becomes E, and so on. Step 4. The result reads the early bird gets the worm. That is plain English, so our guess was right. The key was 6 and the code is broken. So far, every cipher we have seen replaces one letter with one other letter. These are called monoalphabetic ciphers, and they all share the weakness we just used. Because the same plain letter always becomes the same cipher letter, the frequency pattern survives, and we can read it. Block ciphers change the shape of the problem. Instead of one letter at a time, they act on a whole block of letters together, so one plain letter no longer has one fixed cipher letter. But be careful here. Working on blocks is not by itself a cure. The very next cipher we meet, the transposition cipher, only moves letters around inside a block. It changes no letter at all, so every single letter frequency survives it exactly. This is the simplest block cipher, the transposition cipher. It does not change any letters at all. It only moves them around. The key is a permutation, written with the Greek letter sigma. A permutation just rearranges the positions inside a block. Formally, it is a one-to-one function from the set 1, 2, up to m onto itself. To encrypt, split the message into blocks of size m if the last block is short. Pad it with extra letters. Inside each block, move each letter to the position that sigma names. The letter that lands in position sigma of I is the letter that started at position I to decrypt. Use the inverse permutation, sigma inverse, which undoes the rearranging. Our permutation sigma acts on 4 positions. Read the middle row. Sigma sends 1 to 3, 2 to 1, 3 to 4, and 4 to 2. The bottom row is the inverse, sigma inverse. It undoes all of that. It sends 1 to 2, 2 to 4, 3 to 1, and 4 to 3. So the letter sitting in position 1 moves to position 3. The letter in position 2 moves to position 1, and so on. You can check the inverse. Follow any number down the middle row and then back up through the bottom row, and you return to where you started. Let's encrypt pirate attack. Step 1, set it up. Our sigma acts on 4 positions, so we split the message into blocks of 4 letters. That gives PIRA, then TEAT, then TSCK. Step 2, take the first block, PIRA. The letter in position 1 is P, and it moves to position 3. The letter in position 2 is I, and it moves to position 1. R moves to position 4. A moves to position 2. Reading the new block in order gives I a PR. Step 3, do the same to T. It becomes ETTA. Step 4, and TAC becomes a KTC. So the ciphertext is I a PR, ETTA, a KTC. Now let's decrypt. Step 1, set it up. Split the message into blocks of 4. That gives SWUE, then TRAE, then OEHS. This time we apply sigma inverse to undo the scramble. Step 2, the first block SWE becomes USEW. Step 3, the second block TRAE becomes a TER. Step 4, the third block OEHS becomes HOSE. Step 5, read straight across. USEW a TERHOSE. The block boundaries are not the word boundaries, so we look for the real words. It says use water hose. Let's give encryption a clean, general definition, so we can talk about any cipher at once. A cryptosystem is a package of 5 parts. We write it as P, C, K, E, D. P is the set of plain text strings. Plain text is the plain message before we hide it. C is the set of ciphertext strings. Ciphertext is the scrambled message. K is the key space. Think of it as the ring holding every possible key. E is the set of encryption functions. And D is the set of decryption functions. Now the part that makes it a cryptosystem rather than just a pile of functions. Pick a key, call it K. The encryption function for that key is written E sub K. The matching decryption function is written D sub K. The requirement is this. Encrypt P with E sub K, then decrypt the result with D sub K, and you get P back exactly. Lock it, then unlock it, and the message returns unchanged. If that ever failed, the message would be lost, not hidden. Let's fit the shift cipher into that 5-part box, 1 part at a time. Set it up. We say the messages are strings of elements of Z sub 26. That means one number, 0 to 25, for each letter. P, the plaintext set, is strings over Z sub 26. C, the ciphertext set, is exactly the same. K, the key space, is Z sub 26 itself. So a key is one number from 0 to 25, the size of the shift. That is only 26 keys, which is why the cipher is weak. E is the set of functions that take P to P plus K, mod 26. D is the set of functions that take P to P minus K, mod 26. So the shift cipher really is a cryptosystem, just a very small one. So far, every cipher we have seen is a private key cipher. That includes the shift cipher and the affine cipher. If you know the encryption key, you can quickly work out the decryption key. In a shift cipher, they are literally the same number, used with the opposite sign. That means both people must share that secret and both must keep it hidden. And they must somehow agree on it in the first place, without anyone listening. If a stranger ever learns it, everything they have ever sent is open. In the 1970s, people invented a very different idea called public key cryptography. Knowing how to lock a message does not tell you how to unlock it. The two keys come apart. That changes everything. The encryption key can be printed in a public directory for the whole world to see. Only the decryption key stays secret and only the receiver holds it. So anyone can send you a locked message without ever meeting you and without any shared secret. But only you can open it. That is the idea the whole modern internet runs on. Now we meet the most famous public key system, called RSA. Those three letters are the initials of three researchers at MIT. Ronald Rivest, Adi Shamir, and Leonard Adleman. They published it in 1976. We now know that an English mathematician, Clifford Cox, had found the same idea a few years earlier while working for the British government. But his work was classified, so nobody could use it or even know about it. It stayed secret for decades. This is the public key. It is a pair, written n and e, the number n, is called the modulus. You build it by picking two very large prime numbers, call them p and q, each about 200 digits long, and multiplying them together. The two primes must be different from each other, and the exponent e is chosen so that it is relatively prime to the product, p minus 1 times q minus 1. That is exactly the condition that guarantees an inverse exists, and the inverse will be the decryption key. Why is this safe? It rests on one gap. Going forward is easy. Finding two big primes is fast, using the probability tests we met earlier, and multiplying them together is instant. Going backward is hard. Take n with its 400 digits, and try to split it back into p and q. Nobody knows how to do that in any reasonable time. Not with today's methods, and not with today's machines. So the same number is cheap to build and, as far as we know, hopeless to take apart. That gap is the whole security of RSA. Notice the careful wording, as far as we know. Nobody has proved factoring is hard. Let's walk through how you lock a message with RSA. You are given the public key, the pair n and e. Step 1. Turn each letter into a two-digit number. A is 00, B is 01, and so on up to Z. Step 2. Glue all those two-digit numbers into one long string of digits. Step 3. Cut that string into equal blocks. Each block holds 2n digits. We pick 2n as large as we can. The test is simple. Write the biggest block you could ever make with that many digits. the one made of 2, 5, 2, 5, and so on. It must still be no bigger than n. That keeps every block smaller than the modulus. Step 4. Now the message is just a list of numbers, M1, M2, and so on. Step 5. Lock each block with one formula. C equals m to the power e mod n. Let's lock the word stop. The public key is the pair 2537 and 13. Step 1. Factor the modulus just so we can see what is going on. 2537 equals 43 times 59, and both are prime. In real use, these would be enormous, and nobody could do this step. Step 2. Check the exponent is valid. We need the greatest common divisor of 13 with 42 times 58 to be 1. It is. Step 3. Translate the letters. S is 18, T is 19, O is 14, P is 15. Step 4. Choose the block size. 2525 is below the modulus, but 252525 is above it. So we use blocks of 4 digits, 1819 and 1415. Now lock each block. Line 0. The rule is C equals m to the 13th, mod 2537. Step 1. Take the first block 1819. Raise it to the 13th power mod the modulus. The answer is 2081. Step 2. Take the second block 1415. The answer is 2182. So the locked message is 2081, 2182. One important note on how the machine does this. It never works out 1819 to the 13th in full, which would be a 40-something digit number. It uses modular exponentiation, the repeated squaring method from section 4.2, reducing mod the modulus at every step. Now the reverse. To unlock an RSA message, you need a special number D, the decryption key. It is an inverse of E modulo the product P-1 times Q-1. Once you have D, you unlock each block with one formula. M equals C to the power D mod P times Q. An inverse exists exactly because we chose E to be relatively prime to that product. So the condition we imposed back when building the key is what makes decryption possible now. The book gives the full derivation. This is why publishing the encryption key is safe. To find D, you must first know P-1 times Q-1. To know that, you must know P and Q, and to get P and Q from N, you must factor in. Nobody knows how to do that for a 400-digit number. So publishing the pair N and E gives an eavesdropper nothing useful. They can lock messages to you, which is exactly what we want. But they cannot unlock them. Only the person who built N in the first place and so already knows P and Q can compute D. Let's decrypt a real message. Someone sends us 0981 0461. Set it up. It used the same key as before. So N is 43 times 59, which is 2537, and the exponent was 13. The inverse of 13, modulo 42 times 58, which is 2436, is 937. So D is 937. Line 0. The rule is M equals C to the 937th, mod 2537. Step 1. The first block 0981 gives 0704. Step 2. The second block 0461 gives 1115. Step 3. Now split the digits into pairs and read them as letters. 07 is H04, is E11, is L15, is P, the message is help. And a word on how those two powers are worked out. 937 in binary is 1110101001. That is 10 bits, 6 of them ones. So the repeated squaring method needs 9 squarings and 6 multiplications, and it takes the remainder mod the modulus at every step. Nobody ever writes the full power down. A protocol is just a set of messages that two or more people send back and forth to reach a goal. Cryptographic protocols use the tools we have built. Here the goal is a shared secret key, and the surprising part is this. Alice and Bob can build a shared secret while a stranger listens to every single message they send. They start with nothing in common, and they end up with a number that only they know. The classic method for this is called the Diffie-Hellman protocol, and we walk through it now. This is the protocol, one message at a time. Step 1. Alice and Bob agree, out in the open, on a prime p and a primitive root of p. Anyone may hear this. Step 2. Alice picks her own secret number k1 and keeps it to herself. She sends it to the power k1 mod p to Bob. Step 3. Bob picks his own secret number k2 and sends it to the power k2 mod p to Alice. Step 4. Alice takes what Bob sent and raises it to her secret k1. Step 5. Bob takes what Alice sent and raises it to his secret k2. And now both of them hold the same number, a to the power k1 times k2. Their shared key is a to the power k2, all raised to k1, and that equals a to the power k1, all raised to k2. Exponents multiply, and multiplication does not care about order. So both sides get the same number, and neither ever sent it. Now why can the listener not copy this? The listener saw a to the k1 and a to the k2. To combine them, they would have to recover k1 or k2. Either one on its own would be enough, which is why the whole scheme rests on both of them staying out of reach. And going backward like that from a power to its exponent is exactly the discrete logarithm problem we met earlier. When p and r are large, nobody knows how to solve it, so the eavesdropper is stuck. A digital signature is a way to prove who wrote a message. When you receive it, the signature convinces you that it really came from the claimed sender and not from an imposter. This is a different goal from secrecy. Here we are not hiding anything. We are proving authorship. This is how Alice does it with RSA. Her public key is the pair n, and E her private key is D normally. To lock a message X, you compute X to the E, mod n to unlock. You compute Y to the D, mod n. The clever trick for signing is to run the process backward, using the private key that only Alice holds. Step 1. Alice turns the message into numbers and splits it into blocks, exactly as in ordinary RSA encryption. Step 2. But now she applies her decryption function to the blocks. Using her private key D, only she can do this. Because only she knows D, she sends out the result. Step 3. Anyone who receives it applies Alice's public encryption function, using E, which everyone knows. This gives back the original message, because encrypting after decrypting cancels out, just as decrypting after encrypting does. Since only Alice could have produced blocks that open cleanly with her public key, everyone is sure the message came from her. Let's watch Alice sign a real message. Set it up. She uses the same key as before, the pair 2537 and 13, built from the primes 43 and 59. Her private key D is 937. She wants to send meet at noon, signed, so her friends know it is truly hers. Step 1. Translate the letters into two-digit numbers. M is 12, E is 04, E is 04, T is 19, A is 00, T is 19, N is 13, O is 14, O is 14, N is 13. Step 2. Group them into blocks of 4 digits. That gives 1204, 0419, 0019, 1314, 1413. Now Alice signs. She applies her decryption transform to each block. That means, raise the block to the 937th power, mod 2537. Each of these is worked out by repeated squaring. 1204 gives 817. 419 gives 555. 19 gives 1310. 1314 gives 2173. 1413 gives 1026. And notice that she can do all of this on her own. She needs nobody's help, and she sends no secret. So Alice sends 0817, 0555, 1310, 2173, 1026. She pads each block to 4 digits. When a friend receives these, they apply Alice's public transformation, raising each block to the 13th power, mod the modulus. That undoes the signing and returns the original numbers. Split them into pairs, read the letters, and it says meet at noon. So anybody could have read it. Nothing was hidden. But to produce blocks that open into sensible text under Alice's public key, you need her private key D, and only she has it. Now an honest warning, because this raw version is a teaching version. An attacker does not have to start from a message. He can pick any number S he likes, call it a signature, and then compute S to the E mod N and call that the message. That pair passes the check. Real systems fix this by signing a hash of the message rather than the message blocks themselves. And that brings us to the end of Chapter 4. Thanks for watching.